Homework 4.2, Logarithmic Functions, Video 8. Homework due Friday, May 29th at 11:59 p.m. The following video is associated with questions 19 through 22 on the homework. Transformations of logarithmic functions. Before we get to transforming these functions, meaning moving their graphs and possibly reflecting them, I want to remind you of the transformations we saw from homework 4.1 with exponential functions. When we added a number to the end of the exponential function, it caused the graph to move up. When we subtracted from the end, it moved it down. When we added a number directly to the x, it moved the graph to the left. When we subtracted a number directly from the x, it moved it to the right. When we put a negative in front of the whole function, it reflected across the x-axis. And when we put a negative directly in front of the x, it reflects it across the y-axis. So let's take a look at both of these and see if we can analyze the transformations and then use that analysis to sketch the graph. Let's start with f of x equals 4 plus log base 2 of x plus 3. The only reason I wrote 4 plus at the end instead of plus 4 at the end is in the homework, for some reason, when they add a number to the function, they add it to the front. This is the same as log base 2 of x plus 3 plus 4. The fact that it's an the fact that it's a logarithmic function as opposed to an exponential function doesn't change the effect of the plus 4 or the plus 3. A number added at the end, or in this case at the beginning, will still move a graph up. A number added directly to the x, whether it's inside of a logarithm or inside of an exponent, will cause a move to the left. So, we know that this graph is going to move left 3 and up 4. Move what left 3 and up 4? The graph without all those numbers. So for example, if we graphed, and I'll call it h of x only because I've got g of x over there. If we graphed log base 2 of x, well, we already graphed that before. It was the first one that we graphed in the first video. But it looks something like this. It had a y-intercept of 1. And the thing that I didn't mention in the previous video that I now wish I had was the base point. On an exponential function graph, the base point is 1 comma b, because when you put in 1 for the exponent, you get b. But in a logarithmic functions graph, the base point is b comma 1. So in this case, 2 comma 1 would be a point on this function's graph, because log base 2 of 2 is equal to 1. And of course, the x-intercept at 1 comma 0. So let's sketch that graph. Remember, when the base is greater than 1, the graph starts low, has a really quick rise up to the x-intercept, and then just kind of slows its growth. And this graph has a vertical asymptote at x equals 0. And in order to graph the transformed function, in other words, what does it look like after I move it left 3 and up 4? I would keep track of the x-intercept, the base point, 2 comma 1, and your vertical asymptote. Let's move each one in turn, starting with the x-intercept. If we move the x-intercept up 4, so from here to 1, 2, 3 to here, and then left 3, so 1, 1, 2, 3, would put it here. So to keep track of the movement, the x-intercept went up here and then over there, and it now seems to be at the point negative 2 comma 4. That's good enough. Okay. This is much easier to do with graph paper that has all the lines drawn for you. And then if we take the base point, 2 comma 1, base point because the x-coordinate is the base, and therefore log base 2 of 2 is equal to 1. We move it up, left 3 and up 4. Let's move it up 4 first. It's currently up 1. So moving it up 4 would put it up 5. And then to the left 3, it's currently to the right 2, so 1, 2, 3 would put it here. And I believe that point ends up being at negative 1, 5. It's actually easy to locate the new points. Left 3 means subtract 3 from the x, up 4 means add 4 to the y. So for 1, 0, if we subtract 3, we get negative 2. And for 0, if we add 4, we get 4. For the base point, if we take 2 and subtract 3, we get negative 1. And if we take 1 and add 4, we get 5. So you can actually locate the translated points using arithmetic instead of just moving the dots around. Oh, but the asymptote. The asymptote is currently at x equals 0. If I move it up 4, it's still there. It's infinitely long, so moving it up 4 doesn't change it at all. But then I have to move it to the left 3. If I start at 0 and go to the left 3, that puts me at negative 3. And so that vertical asymptote is now here at x equals negative 3. And if I just reconnect the dots, what's the x-intercept? Well, that's a little bit beyond what we can do right now. I challenge you to try to find it though, it's not impossible. Remember, the x-intercept is whatever makes this equal to 0, so I'm curious if you could solve it. At some point we're going to solve those. That'll be the second to last video series. But for now, left 3, up 4, everybody move, including the asymptote. Now what about this one? Well, it's natural log, but remember, natural log by definition means log base e, and recall that e is about 2.7, so it's greater than 1. So it is logarithmic growth. So we can do the same thing here. But let's identify the transformations before we draw anything. A minus 2 on the x, subtracting a number on the x moves it to the right. So this minus 2 means we're going to move to the right 2. And what does a negative in front do? Reflect across the x-axis. So we're going to reflect across the x-axis, and then we're going to move to the right 2. And for those two, it doesn't matter what order we do them in. The main reason I don't do stretching is because the order matters. If we just move and flip, the order doesn't matter. It's not entirely true, but let's just pretend I didn't say that. Okay, so let's start with the graph of natural log of x, whose x-intercept is 0. Now, if we want to locate the base point, we have to go over about 2.7. That's about here. So there's e, 1. You know what? Let's just call it 2.7, 1. It's e, 1, but for the sake of moving it around, let's call it 2.7. And of course, the x-intercept is 1, 0. We still have the vertical asymptote. And sorry, something was just going through my head. Pretend that didn't happen. And we start low, shoot up to the x-intercept, and then slow the growth. That is logarithmic growth. And now let's do the things we need to do. We're going to reflect across the x-axis and move to the right 2. Let's start with the reflection across the x-axis. The x-intercept is on the x-axis, so it's not going anywhere. But the point 2.7, 1, when it gets reflected at the x-axis, would go to 2.7, negative 1. Now we're not done moving things around. That's just the reflection across the x-axis. Now we need to move everything to the right 2. So where would this x-intercept go if I moved it to the right 2? Here at 3, 0. I'm picturing the graph so that when I draw it, it won't go through the ordered pairs. And if I move 2.7, negative 1 to the right 2, where does that land? At about 4.7, that's about here, at about 4.7, but it's still down 1. What about the asymptote? The asymptote is currently at x equals 0. Reflecting it doesn't change it, it lands on top of itself, but it moves to the right 2. So if it's at x equals 0, then it's going to go through x equals 2. So let's get rid of these intermediate points. I need to, well, think about it. This started low and then went up, so now it's going to start high and go down. So start high, zip down to hit the x-intercept, slow the decay, and there you go. And again, in the homework, it's going to be just like the exponential functions. You select the transformations, you slide sliders or click buttons, you click a button for a reflection. Just be sure that when you do that, you remember to draw the asymptote as a dotted line. And that's the end of this section. I think this is going to be a pretty easy homework section once you wrap your mind around what a logarithm is asking. And if you have any questions, then get a hold of me.